Good day. My name is Mohammed Al-Siddiqui, and today I will be presenting my research project titled Reentrancy Detection in Smart Contracts using deep learning techniques. Now, in 2016, the DOA hack exploited a reentrancy vulnerability in smart contracts that led to over $60 million being stolen. This incident highlighted why my research matters. If we can detect reentrancy vulnerabilities more effectively, we can prevent catastrophic losses in blockchain systems. Now, what is blockchain? Why are blockchain networks important in the first place? So blockchain networks avoid the involved with centralized networks by using nodes that work together to maintain and secure a shared transaction history without relying on a central authority. Now, this takes out any issues that could be faced when dealing with these central authorities. Now, smart contracts are the tamper-proof and self-executing computer programs that are written in Solidity, and they cannot be altered once they've been deployed. Here is a diagram, Avatar's diagram, which shows how a smart contract transaction works, where both parties present their condition and the response rule are present during the smart contract. And this transaction is put into blockchain, which contains the multiple nodes. Now, this leads to, however, despite the secure nature of smart contracts, they are not free from vulnerabilities. Some of these vulnerabilities include integer overflow, timestamp manipulation, access control flaws, and reentrancy attacks. These four are the most common vulnerabilities that smart contracts have to deal with. Now, smart contracts, as I mentioned earlier, are meant to be tamper-proof and trustless, but vulnerabilities like reentrancy attack undermine this promise. Which leads us to the question, what is a reentrancy attack? Now, these reentrancy attacks occur when two smart contracts interact, and malicious contracts repeatedly call the vulnerable contract. Now, the vulnerable contract then transfers funds before updating its state, and as a result, the attacker repeatedly drains funds via recursive calls. So the attacker keeps making these calls, and the vulnerable contract keeps sending funds, thinking that it hasn't yet done this. Now, a popular example of the harm that reentrancy attacks can cause is the aforementioned DAO attack of 2016. Now, I've attached a diagram which shows the timeline of the DAO attack. When in 2014, the project Ethereum is founded, in 2016, the vulnerabilities of the smart contracts are made public, and that the flaw lays in the code. In 2016, the threats were dismissed by the DAO's founders, stating that there's a workaround the loophole has been created. A workaround the loophole had been created in the framework, and later in 2016, the DAO was attacked, just a few days after they dismissed the threat. Over the course of the next 36 hours, the community wars as the DAO was drained of 228,500 Ether per hour, leading to a loss of about $60 million. Now, um, like most vulnerabilities, tools do exist to detect these vulnerabilities, and a few of the most popular are are listed here, which would be Slither, Mithril, and Oyente. Now, these tools, however, are limited in their detection ability and rely on static analysis and tend to have a large amount of false positives or tend to miss the deeper patterns that these vulnerabilities follow. Which leads us to the question, why use a deep learning approach? Now, deep learning allows for hidden patterns to be captured and allows for both semantic and structural analysis. The model designed in this project uses a hybrid approach to capture data from not only the code's text, but also the function call graphs that let it analyze the structure of the smart contract itself. Now, the aim of this project was to develop a hybrid deep learning model that combines transformers for the semantic part and GNNs for the structural part. The objectives that were laid out were to develop the transformer-based model for the semantic analysis, to develop the GNN model for the structural analysis, to integrate both models, and to compare the hybrid model against these two baselines. Now, the methodology of this project. The two core models that were implemented were a baseline by LSTM plus transformer model and the hybrid GNN. The workflow of the model is shown here, where the dataset is loaded, the graph representations were created, the GNN was trained, the graph embeddings were generated, these embeddings, and then the models were combined into the hybrid model, and the model was evaluated. Now, dataset preparation. The dataset was taken from Kaggle as a CSV file and contained 12,000 smart contracts. The file contained the bytecode of the smart contracts, but the individual Solidity files were not available. Some of the smart contracts were clean, some contained, and others contained very different vulnerabilities. Each smart contract was labeled to show which vulnerability it contained. And after the dataset was cleaned, I made a balanced sample set of 1,200 contracts that were half of the sample dataset contained the reentrancy vulnerability and the other half did not. The code was then tokenized to 10,000 words and padded to 1,000 to a length of 1,000, and the sample set was then split into training, validation, and test splits, with the training set being 70% of the codes, validation set comprising of 15%, and the remaining 15% was the test set. Now, for the graph construction, each smart contract was parsed into a graph, and the edges represent the function calls and the control flow links, as these explain how the execution moves between different parts of the contract. The nodes represent the functions and Solidity keywords such as call.value, as these are commonly targeted by um, another thing that was part of the DAO attack, where call.value was what was targeted by the attackers. And then these graphs are stored in the JSON files. Now I've also attached a snippet of the code to show these parts. And these are the keywords that we were looking out for. Now, for loading the dataset, GNN training was done by using two-layer graph convolution networks, or GCNs, that were trained to capture the structural dependencies between function calls. And the training ran for 10 epochs, as you can see. The training ran for 10 epochs and with Atom optimizers, and it was relatively quick. The weights were saved and to be used later. Then for the GNN embeddings, the saved weights from the model were used to generate 64-dimensional embeddings for each contract, and these embeddings were saved as numpy arrays in a .npi file. I found that 14 of the graphs had no edges, and so these graphs were separated and their embeddings were saved in a separate file to avoid affecting the final model. Now here you can see the code snippet for the training process, where the embeddings and the skipped indices were kept in separate lists, and the embeddings were then saved after generation. Then for the hybrid model itself, as mentioned before, the hybrid model has two branches. The transformer branch that learns the semantic features and from the raw contract code, and the GNN branch that uses the embeddings from earlier. Now, before combining the two branches, the embeddings were normalized using robust scaler to stabilize training and to look out for outliers. And various scalars were experimented with, but this had the best results. Now, after concatenation, the results from both branches were passed through dense layers for binary classification. Now, here's also this code snippet for this, where you can see the GNN inputs being the embeddings, the transformer layer here, the GNN layer here, and the hybrid model, which with early stopping and early plateauing applied in both. Now, as for the hybrid model workflow, it can be seen in this flow chart, where you can see all the processes that the transformer model went through and the processes that the GNN went through, and all the processes that I mentioned earlier. Now, as for the result, here we can see the classification report and confusion matrix for the initial transformer-based model, and here are the same for the final hybrid model. Now, it's a bit difficult to compare the two confusion matrices, as the transformer-based model had a different training test split of 80% training and 20% testing without a dedicated validation set. And the hybrid model also included threshold tuning, which what's it called? Which which let us get the results from when the model was performing at its best. Now, upon looking at these two classification models, it's quite obvious that the hybrid model outperforms the transformer and by LSTM model significantly. Now, we can see that the hybrid model boasts a higher F1 score of 83% as compared to 0.83 as compared to 0.78 over here. And it also has a higher recall of 0.97 as compared to 0.91. These numbers mean that it detected nearly all vulnerable contracts with very few false negatives. However, the precision, while being better than the initial model, is still not ideal at 0.74 due to some false positives that can be seen in the confusion matrix, where, as you see, there's still a significant number of false positives, even though there's almost no false negatives. Now, for the achievements and the limitations of this model, so the hybrid model displays a strong performance, especially in recall, which is essential in the security context, as it's better to overflag than to miss vulnerabilities, better be safe than sorry. And as for the limitations, the biggest limitation, in my opinion, was the fact that the data set used came in the form of a CSV file and didn't contain the individual Solidity files themselves. This made it very difficult to use it to test the traditional tools, as those require the Solidity file themselves. While it's possible to construct these Solidity files from the data and CSV files, it's very tedious and it's quite time consuming. And it has a level of complexity that unfortunately is beyond me. Now, for future work recommendations, as mentioned before, I was unable to test against traditional tools, and so it would be ideal for future researchers to do that for better benchmarking. Future researchers could also look into what I feel is the direction that is most relevant, and that would be the use of detailed prompt engineering in order to improve feature selection. I've discussed this in a lot more detail in the report. As I mentioned, this is what I feel is the best direction to go forward in. Another direction for future work would be to manually separate the patterns that resemble vulnerability. I mean, manually filtering out the patterns that resemble the reentrancy vulnerability before normalization. However, this can be quite complex and would require a very deep knowledge of Solidity codes and patterns. And finally, another future researchers could use richer graph enhancement techniques, such as ASTs, for more complex graph construction. Finally, to conclude, I would like to say this project shows that the combining transformers and GNNs leads to a more effective detection of reentrancy vulnerabilities than using only one or two approaches. By capturing both semantics and structures, the hybrid model achieves strong results and I feel provides a strong foundation for future researchers and ultimately for building a safer blockchain applications in general. Thank you. This is the graph generation code, and I'll now run a demo of my running the whole code. So I've moved to the directory containing all the files, and now once I run it, it's created text.graphs, which is the folder containing the graph data. Now this is text graph dataset. This file does not need to be accessed as it's ran through the other codes. So now I will train the GNN using the text graph dataset, the graphs in the data generated. So this takes a few seconds. So it's finished running the GNN, and here we can see the classification report that it generates. Recall of 0.71 means recall of 0.73, F1 of 0.71, and precision of 0.68. Nothing amusing, but the model weights have been saved to this file. Now, after that, I can run, sorry, I can generate the graph embeddings. So here we can see in the file to generate the graph embeddings, this takes the graph data again from the same text graph data set and saves the embeddings into the NumPy array and gives us an idea of the shape of the array at the end. So when I run this, now as we can see here, the model has ran, I mean the graph embeddings have been generated, and these were it lists out all the graphs without edges. And the saved GNN embeddings were saved to this, and this is the shape of the NumPy array that was created. Now, after this, we go on to the hybrid model, which, as we can see here, reads from the CSV dataset. This is for the transformer branch. Then it loads the GNN embeddings that we just made and skips the the graphs with whose embeddings we found, I mean, the graph embeddings of the graphs that we found to not have no edges. This is the train test split. It applies the robust scalar and the class weights, balances the weights, and then the final model, which concatenates everything, is ran, early stopping and reduced plateauing are implemented, and the model trains itself based on our inputs. Threshold tuning then starts up, and it runs on these thresholds to look for the best threshold based on the F1 score, not the accuracy. So it tells us what the best accuracy threshold was, so we can see what the highest accuracy was while running, and it also shows us what the best F1 threshold was. I also implemented a function for it to print out the embeddings before normalization and to print out the embeddings after normalization so we can see exactly how normalization affects the model. Now I'll now run this model and show the results. So now the model is done running, and here we can see all the 10 epochs. Now, in the final epoch, an accuracy of 0.805, loss of 0.44, validation accuracy of 0.81, and validation loss of 0.45. These will be compared better with the graph later. And the learning rate stayed the same. Even though plateauing was involved, it didn't need to. Early stopping and learning rate didn't plateau, so it didn't have to change. Now, while testing with different dense layers and dropouts, um, sometimes these two were triggered and they did need to be involved. But like for example, when I used 20 epochs, it did include early stopping. And when the dropout was 0.3 instead of 0.4, the learning rate plateaued. However, these were in this case that didn't happen. And for the threshold tuning, here we can see the threshold going from 0.3 to 0.7. The best accuracy threshold here was 0.3, and the best F1 threshold as well was 0.3. Now, here's the final accuracy classification report with an F1 score of 0.83, recall of 0.87, and precision of 0.72. Now, while these figures aren't exactly the same as the ones shown in the presentation, the model doesn't perform exactly the same every single time, obviously. But we can see that they are quite close to those values as well. This is now the um, confusion matrix can be seen here, where we've got the same thing, very low false negatives, very decent amount of false positives, but good detection rates. Then we can also see the next would be the ROC curve for the threshold tuning, where we can see the 0.3 being the best, 0.3 as being the best for both accuracy and F1 score, and they both decline over time over the different thresholds. Then the next one, the next metric to be shown will be the accuracy and loss curves, where we can see over time they combine the accuracies of both the training and validation accuracy get closer to each other, and the training and loss also converge. And as we can see, there is almost no overfitting and underfitting in either of these. And those are all the visualizations created from the graphs. Also, the data on the GNN embeddings can also be seen here at the bottom, as these come in after these are produced after the visualizations. And so you can see the difference between the embeddings before normalization and after normalization, and after normalization clearly is closer to what we would like. Thank you. That is all for the demo. And thank you very much.